give you the information about a 20 Newton block, and we know that a 20 Newton block has a weight of 20 newtons. Thus, it's got a mass of 2. Remember, we know that weight equals mg, so instead of giving you the mass, they gave you the whole mg. So you just take away g and you're left with the mass. So after that, it's kind of straightforward. We're pushing it with some applied force, friction is opposing it, and that's causing this to accelerate. So you take your free body diagram into your algebraic equations, and eventually you get this in the abstract. We know that we're pushing it with some applied force, friction is opposing it, and that's going to push that mass at a certain acceleration rate. In this case, the normal force equals mg because it's just chilling on a flat surface. And so we replace the force of friction by mu n, and in this case, n is mg, and so we just get that equation, and then we plug it in. Okay, this one, very similar. It's just trying to fool you. It does remind you that we know that the gravity on the moon is 1/6 of the gravity on Earth. Okay, that's fairly worthless because we're not actually lifting the block vertically in this situation. We're just accelerating it across a frictionless table. When we take this block of mass to the moon, its mass doesn't change. And so if we want to accelerate it horizontally, it's still the same thing. It's the same force to accelerate the same mass at a certain acceleration rate. Now, if we wanted to lift this block vertically upward, well, that would change everything because then we'd be lifting against the force of gravity. Here, we're simply pushing it, and based on its inertia, it gets an acceleration. So totally a trick question. Remember, changing the force of gravity does not change the mass. Okay, so first thing, we got to decide whether this box moves or not. To decide whether it moves or not, we're looking at the coefficient of static friction. Static meaning stationary, kinetic meaning motion. So we got to overcome static friction. Remember, if you think about the free body diagram, it would look like this, and we set up this equation. If our applied force is bigger than the force of friction, then we will accelerate it. Once it starts accelerating and moving, we would, instead of using static, we would then use kinetic friction. So in this particular case, look, the applied force was 344. The most friction can be is mu mg, and so it looks like friction is 400. So you got to push harder than 400 newtons or else this thing will not move. And so since you only pushed with 344, your conclusion is it didn't move. If it pushed, if FA was bigger than 400, then it would have moved. All right, this is the definition of Newton's third law. This is you punching the wall and the wall punching your hand back, thus breaking your hand. This is a big car, or this is like a big truck hitting a small car. It doesn't matter. They both have the same force acting on them. You have to believe in Newton's third law that says there's equal and opposite reactionary forces. So if a big person and a little person are standing next to each other and they push each other, and it actually doesn't even matter who pushes. The heavy person can push, the light person can push, doesn't matter. Regardless, the forces are going to be the same. However, the acceleration rate of the light person will be twice the magnitude of the heavy person. Look over here. If this is the same for both people, but one of them has half the mass, they're going to get double the acceleration of the other person. That's like the doubling, tripling thing. Again, the first piece is that the force has to be the same. It doesn't matter who pushes who. Newton's third law. And then after that, well, a bigger force applied to a smaller mass will cause a bigger acceleration. Number 5. All right, here's all the things that could happen. Think about it. If all of these forces were acting in the exact same direction, all right, so there are 4 of them. Let's pretend all of them were pushing with 10 newtons, all of them to the right. That would have a 40 Newton force. That would be this scenario. 40 newtons causing a 5 kilogram thing to then accelerate at 8. That means 8 is the biggest. You can't produce a bigger force, or you can't produce a bigger acceleration considering we aligned all 4 forces to go in the same direction. We certainly can produce smaller accelerations, like we can have all the forces totally balance each other out, thus producing no acceleration. But there's no way we can get 10. To be able to get a 10 meter per second acceleration, we'd have to have a force of 50. We can't have a force of 50. So this one makes no sense. Can't get that. We can get all these other ones depending on how we arrange the forces. All right, this one, please draw the free body diagram. If you draw this, you'll lead to this equation and you'll realize that the tension's not 49. 49 is the weight of the object. Remember, a 49 Newton object has a mass of 5. And so what do you want to do? Well, you want to lift it with a certain tension. You got to overcome the weight and then accelerate that mass at that rate. They just give you that you want to accelerate it at 9.8. So you're basically like doubling kind of gravity. And so it makes sense then that your tension is double the weight. You got to overcome gravity and then accelerate it at the rate of gravity upwards. So you got a tension of 98. Okay, so if you look at it, this is the given piece of information. And it's telling you that the velocity is something t squared. Look, the velocity is some quadratic. So I don't care what it is. So k is just some number. The velocity is some t squared. If you take the derivative of velocity to get acceleration, that means acceleration is some t, meaning the acceleration is linear. But we know that F equals, oh, this doesn't like me doing this, F equals ma. Well, if F equals ma and a is linear, then the force will be linear, which is why I circled the linear force. Velocity is related to acceleration. Acceleration and force are off by a factor of m. So if this is quadratic, this has to be linear. Little calculus. Same thing here. Here they give you the velocity as a function of time. We take a derivative to find acceleration. We know that then force is equal to ma. So you just take this acceleration and multiply it by a mass, and now you have an equation for the force. Okay, this is the force as a function of time. Okay, so now we have a drag force, and it tells you that the drag force has a magnitude equal to BV. Okay, so if our ball is falling down, gravity's pulling it down, and the drag force is pushing it up. It's resisting it falling. So when you draw F equals ma, we would say mg down minus bv up equals ma. If the weight of the object is bigger than the drag force, then it will accelerate. And so all you have to do then is solve for a. Right, you solve for a, and they do a little algebra. So they do mg over m minus bv over m, and so the mg's cancel for that lead term, and they just get a g. Okay, little algebra, but again, they give you this resistive force. You know it's going up. Okay, 10. Draw a free body diagram, right? It's saying that you want to lift this thing. So you have a tension up, and you got weight down, and there's your equation. T up minus mg down equals ma, but they give you some maximum breaking strength of the rope. That means that's the biggest the tension can be, which leads you to the biggest the acceleration can be. So if the tension can only be 50, just plug in 50 for that. The weight of the block is 30. Remember, if the weight of the block is 30, the mass of the block is 3, and then you get this equation and you solve for acceleration. There's no way the acceleration can be bigger than that because the tension can only be 50. If it's any bigger than 50, then the rope will break. Which of the following could represent the velocity? What's happening here? Oh, a constant net force. Okay, so again, it's one of those, if you get a constant net force, for a little bit you get a constant acceleration, which will then lead you to some velocity. And if you do each of those forces for 1 second, they're going to increase the velocity by the exact same amount. And so your it doesn't matter which one you did first. At the end, if I gave you a horizontal force for a little bit and I gave you a vertical force for a little bit and I gave you the same force in the same time, I would have accelerated you in those directions the same amount. Thus, those two things have to be equal, and my vector would have to point exactly at 45 degrees. If I gave you a bigger force in the y direction, or I applied that force longer in the y direction, then it would look like this. If I did it longer in the x direction, it would look like this. This is only you moving horizontally, so you would have got no vertical forces on this one, and this one, of course, would have been no horizontal forces. All right, so what they tell you is that you know you are accelerating down this ramp under the influence of gravity, and we know that gravity down the ramp is this mg sine theta. So the only force acting on you in the x-hat direction is mg sine theta, so mg sine theta equals ma. Sine theta, sine of 30 degrees is 1/2, so then g sine theta leads you to an acceleration of 5. This is old school. That's going back to unit 1. That's saying that if I accelerate like the track girl, d equals 1/2 at squared. There's no initial position, there's no initial velocity, so it's the standard one-dimensional equation, just as 1/2 at squared, and I just plugged in. I found this was 20 because of trig. Remember, if this is 10 and this is 30, I can do sine of 30 equals 10 over what, and I can find that. Or you can realize it's a special right triangle. If this is 10, this has to be double. Remember, the hypotenuse is always double the short side in a 30, 60, 90 triangle. And then I plugged in. Okay, these two questions are together, right? This one, it tells you that you know the time, and now you want to find the velocity. But again, this is old school. Look, if I want to know how fast I'm moving, I want to know how fast I was starting, what was I doing, and for how long. I knew I have an acceleration of 5, and I did it for that amount of time, so boom, I get this. Again, you need to know that the square root of 8 is around 2.8, because the square root of 8 is the square root of 2 times 2, and the square root of 2 is 1.4. Those are values that you should know, meaning the square root of 2 is 1.4, and then you can get this in your head without a calculator. You get a calculator, but I'm just saying you should be able to do it without a calculator. You can also do the v squared equation because you know the acceleration rate and you know the distance. It's probably even easier. This one, okay. They're faking you out because they don't want you to rotate the coordinate system, and they want you to think about the acceleration here. Well, if we don't rotate it, yes, it is accelerating to the right and it is accelerating down. So if you look at Vx should have a linear thing, because remember, the slope on a velocity versus time curve is acceleration, and we have a constant acceleration to the right. So here's your choice. If the velocity is linear, then the position x is going to be quadratic. Constant acceleration, linear velocity, quadratic, nice curving position function. Again, calculus here. This. Constant acceleration, which would be like, mg sine theta type stuff. This, and then this. They all go together. Okay, so they give you a trick question because they don't actually want the distance from 0 to 2. They want the distance from 1 to 2. Okay, so let's figure that out first. It says it goes 1 meter in the first second. So that's when I do this. I know that this equation describes what happens when I'm looking at a distance and I have an acceleration with no initial velocity and no initial position. So if I go 1 meter in 1 second, I must be accelerating at 2. If I'm accelerating at 2, how far would I go for the first 2 seconds? Okay, we'll do the same thing, except now use a time of 2. And I get 4. Now I can answer the question. I went 1 meter for the first second, and I went 4 meters if I covered 2 seconds. So how far did I go during that second? Well, then I only went 3 meters. Again, this is for 0 to 2. This is from 0 to 1. This then, the difference, is from 1 to 2. All right, look at this. You're like, first of all, this is stupid. Gravity is always down. This is stupid. The normal force is always normal. So these are dumb. Okay. Now, if you look at these, like I haven't even read the question yet. These components are labeled wrong. mg sine theta is not this way, and mg cosine theta is not this way. mg sine theta is down the ramp, and mg cosine theta is in the ramp. So that's stupid too. So dumb. Can't be right. Okay, now let's look at these. This looks like it's pulled up the ramp. Look how big this applied force is. This guy is then accelerating down the ramp. Or at least it's sliding down the ramp. If you're not sure it's accelerating, you'd have to compare gravity to friction. But this guy for sure is going up. Look how big that force is. It's definitely going to be bigger than little old friction and gravity. So which figure best describes accelerating up the ramp? That guy. Right? It looks like that is bigger than that and that. Which figure represents it's at rest? Well, it's got to be C. Somehow they're claiming that that down the ramp piece, oh, kind of tilted on me there. That down the ramp piece of mg is the same size as friction. And so it must be at rest or constant speed. Remember, these are the same thing from a force perspective. If you tell me that the net force on an object is 0, I will tell you that the object is not accelerating. I cannot tell you whether the object is sitting or it's moving at a constant speed, because that's the same information. Again, if you tell me that the net force is 0, I will tell you that it's not accelerating. That's all I can tell you. And so an object at rest and an object moving at constant speed have the exact same free body diagram. So when you look at this guy right there, you cannot tell whether it's at rest or whether it is at a constant speed. All right, you look at this thing. The only thing making this thing move, if I'm looking at a system perspective, the only thing making it move is that guy's weight. That's it. That guy pulling it down. What's resisting it? Nothing. If there was friction up here, well, then we'd have to do like a mu mg term up there. But if there's no friction, there's no force up here. This guy's weight down is totally balanced by the normal force up. So we're good there. So this force is making the system accelerate, and you just solve for A. Okay, no friction, and so you can break this up really easy. Remember, this rope is making all 3 of those boxes accelerate. This rope is only making those 2 boxes accelerate, and this rope is only responsible for pulling 1/3 of the total mass. So you could go through the whole math of it, but this one is way easier because they just want you to realize that if this is some F, that has 2/3 of it, and that gets 1/3 of it. Okay, I mean, we'll maybe even look at this question at Newton's third law of forces more, but each rope is responsible for accelerating the mass behind it at a certain acceleration rate. This has triple the mass that this guy does, so this only gets 1/3 of the force. Okay, so we're pushing this way, and when we push on the 3 kilogram box, we have no idea that the 2 kilogram is there. We just think we're pushing something with 5 kilograms of mass. So when you look at the system equation, we're pushing at 20, and we're pushing 5 kilograms. These boxes could be on top of each other, they could be bolted together, and they could just be sitting next to each other. We don't care. We don't even see the other 2 kilogram box. We just know that we're pushing something with 20, and we're pushing something that has an inertia of 5 kilograms, and we will then accelerate it at 4 meters per second. But if you look at just the first block, so now we're looking at the first block only, it's being pushed by an FA. It's being resisted by this 2 kilogram because it's going to push back on it. And so that's F23. That's the force of the 2 kilogram block on the 3 kilogram block. And that's what we want to figure out. We're pushing it with 20. We know we accelerated at 4, and we know we're only pushing 3. And so what does this force have to be? Well, 20 minus what equals 12? Well, 20 minus 8. So this guy must be pushing back to the left 8 newtons, which also means that the 3 kilogram box is pushing to the right on the 2 kilogram box with 8 newtons as well, which again, think about it, 8 newtons pushing 2 kilograms. Oh, look at that. It produces an acceleration of 4. Again, we can look at that, but this is another Newton's third law question where these internal forces have to be equal and opposite. The 3 pushes the 2 with 8, the 2 pushes the 3 with 8. All right, this is like an Atwood machine, right? This is the bigger mass, so this weight is bigger than this weight, and so the system says that this guy is beating this guy. So the difference between the left weight and the right weight, that gives the net force on the system. So the net force on the system causes the system's mass to accelerate at a certain rate. And I just plugged in numbers. All right, looks like I'm pushing down on this box, right? So if I'm pushing down on this box, I'm going to make the normal force even bigger, right? We know that the normal force has to be balanced. And so the table is going to push up against somebody pushing down on it and the weight of it down on it. So the normal force is going to equal the sum of those two. And so the frictional force is going to equal mu times the normal force. Well, mu times the normal force is that. And so if you just want to find the frictional force, you just multiply all that out. Again, you're making friction bigger by pushing the box into the table. Okay, so we're accelerating this thing upwards, right? The rope itself can't be bigger than 600, so they're telling you the maximum tension in the rope. You're pulling up, weight's pulling down. There's your free body diagram. That's your algebraic equation for vertical. The tension, if it's bigger than mg, will cause the box to accelerate. And then it says, and it's true. And then everything else is just told to you, right? So that's the acceleration the helicopter can have. If it's bigger than that, if you tried to get a bigger acceleration, it would require a bigger tension than 600, which would snap the rope. All right, so we're taking this box and we're pushing against the wall, and this is the free body diagram we get. Friction is, if the object would start to slide down, friction would oppose it upward. You're pushing to the right, the wall pushes to the left, and all of these things are balanced because you want to keep it from slipping down. And so you just set these equal to each other. The normal force equals Fa, which means friction equals mu times the normal force, and so it's mu times Fa. And then we can just solve. This is for how hard you'd have to push against the box to make it not slide. The harder you push, the harder the bigger the normal force is, the bigger the normal force, the bigger the friction can be, and we can have those things balanced. Okay, so we're pulling it to the right, but we're also pulling it up and left for whatever reason. It looks like the normal force and mg are balanced, so we don't have to worry about friction, and we just want to figure out the horizontal acceleration of the cart. And so I actually picked the wrong direction, right? And that's why my acceleration comes out negative. It's totally okay. If you switch these, good for you. That's fine. I actually prefer you to just do what I've said, that if you call this one F2 cosine 60 minus F1 equals MA, you would have got a positive 1/2, which is totally fine. They want to know the magnitude, which means they just want to know the size of the acceleration. Again, if you end up like me and you picked the wrong direction, you're going to get a negative, which just means, dude, it didn't accelerate to the right. It actually accelerated to the left, which is fine. Okay. All right. So this is just our classic box on a ramp. This is the equation we've gotten 100 times. We know that mg sine theta is down the ramp. Mu mg cosine theta is the frictional force. And if down the ramp force is bigger than the frictional force, we're going to get an acceleration. So if you look at this, the m's can cancel. And I know I'll get an acceleration if this is positive, meaning if g sine theta is bigger than mu g cosine theta. So in this particular case, I can look at sine of 30, and I can show you that it's bigger than mu cosine of 30. And so since this is bigger than this, the acceleration will be positive, and it will accelerate down the ramp. Again, you can make up a mass if you wanted to. Then you're just saying that mg sine theta is bigger than mu mg cosine theta. It's all that matters. Okay, this is, you can figure out the angle if you need to. This is just me kind of doing it without a calculator. Remember, some of these questions were so old that you did them without a calculator. So sine of theta is just opposite over hypotenuse. This is a 3, 4, 5 triangle. And again, it has nothing to do with the 5 kilograms. 3 meters, 4 meters would be 5 meters. So that's where these values come from, just Pythagorean theorem type stuff. So what do I have here? I want to pull the block up with constant speed. All right, as soon as you see constant speed, you got to write acceleration of 0. So you're going to pull, and you got to beat gravity down the ramp, and you got to beat friction down the ramp. And again, these are the exact same thing, except in this case, both gravity down the ramp and friction down the ramp are fighting against me pulling up the ramp. And again, you want to pull it up with constant speed. So you need this force to be equal to that sum. Or the same thing as saying this minus this equaling to 0. So I just put in all the numbers. Sine theta is just 3/5, cosine theta is just 4/5, and I slapped in the number. Now, if you actually found the angle, you could do inverse tangent of 3/4 and find the angle, and then you could take sine of that angle and cosine of the angle, and you'd be fine. You'd just be doing it with a calculator. I just never even found theta. I just knew that sine theta was 3/5 instead of actually finding the theta. Think that through. This way is a little easier, but if you actually found the angle, that's fine. You would have got the exact same answer. All right, what's making the system move? This guy's weight, which is right here. What's opposing it? The friction of it scraping right there. That's it. This guy's weight is totally supported by the normal force. It's not battling against you. So it's this guy's weight versus this guy's friction, causing the system's mass to have a certain acceleration. And so I just plugged in. Which string is has to be the biggest? Dude, and this one, that's got to pull all of it. This has to pull 5 kilograms of it. This only has to pull 3 kilograms of it. This has to pull all 6. This rope, it doesn't even know that these ropes are here. It thinks that all these guys are just hooked together and it's pulling 6 M worth. Again, very conceptual. This one and a previous one are very similar in terms of understanding how the tension in a system would work. And that's it. Hopefully that video helps you out. Again, if it doesn't, then certainly you can ask me anything you want in class.